Hi, this is Barrett Givens, and in this video, we're going to do two more examples of sets that are bases on another set X. Okay, so in this example, we're just going to let X be any infinite set. So X could be like the reals, it could be the integers, it could just be anything that's infinite, okay? It could be R2, complex numbers, anything at all. And we'll let we'll let script B, cursive B, be the collection of all capital B subsets of X such that B complement is finite. So it's sets whose complement is finite. Sets whose complement is finite. Okay. And so let's think about just kind of for some intuition. So for example, if X were equal to the integers, capital B being the integers minus the point 0 would be basic open. Or if capital B were something like the integers minus 1, 2, 3, that would be basic open. But if B were equal to the collection of all even numbers, then its complement is all odd numbers, and that's not finite. So that would be not basic open. Okay? So just to give you a little sense of what the basic open sets look like. The basic open sets just basically have to look like the set X, but with a finite number of points taken away. Okay. So let's think about the two parts of the definition of being a basis. So first of all, we have to say, okay, let's let A be an element of capital X. Is there a basic open set that contains A? Do we have coverage of this full infinite set? Well, I actually think that there's a very straightforward way to do this. Let's just let capital B be the whole set X. If capital B is the whole set X, what is the complement? The complement is the empty set, which is certainly finite. So the whole set X is a basic open set. And obviously, A is in it because A is in X. Okay? All right, so that's the first part of the definition. Now the second part. Let B1 and B2 be sets in B. And let's let little c be an element of B1 intersect B2. Okay, so B1 complement is finite. By the definition, being in capital B means its complement is finite. So B1 complement is finite. And B2 complement is finite. So think about like this, these examples over here. These could be like the two sets, okay? And one of them, the complement is just the set 0, and the other one, the complement is the set 1, 2, 3. What I want to know is, what does B1 intersect B2 look like? What is the complement of B1 intersect B2? What is the complement of B1 intersect B2? Well, we have something called De Morgan's laws for this. This is B1 complement union B2 complement. And I'll draw a Venn diagram in a second just to review that, but that's De Morgan's laws. So the complement of B1 intersect B2 is the union of the complements. And each of those complements are finite. So this is a finite set unioned with another finite set. When you union up two finite sets, the answer is still finite. Okay, and so in this case, B1 intersect B2, the complement of B1 intersect B2 is also finite, which means B1 intersect B2 is also in B. And so we'll let B3 just equal B1 intersect B2. So little c is in B3. which is certainly a subset. It's more than a subset, it's equal, but all we need is subset because that's the definition. All right, and then real quick, because I promised, the um, the Venn diagram for the De Morgan's laws. So here I have my B1 and B2. And let's say B1 intersect B2 is this little bit in the middle. And B1 complement, so let's say B1 is the one on the left. B1 complement is everything that's outside of B1. So the pink is B1 complement. The blue is B1 complement. The blue is B1 complement. Okay. Now B2 is everything outside of B2, which I'm going to say is the one on the right. So this peachy color is B2 complement. Okay. So B1 intersect B2 is the little green, like, um, oval shape. Its complement is everything outside of that. B1 complement is everything outside of B1. So that's the part that's blue. And then B2 complement is everything outside of B2. So that's the parts that's peach. So the left-hand side of this is whatever is outside of B1 intersect B2. So that's everything out here. The right-hand side is everything that's either blue or peach or both. And those are the same. Okay, so that's the De Morgan's laws. That's the illustration of De Morgan's laws that justifies this statement right here. Okay, so point is, this is a basis. We have a basis here. Second example. Second example. Let's let X be any set at all. It could be just the set 1, 2, 3. It could be the set of all reals. It could be anything. Okay. And we'll let B be the set of all singleton point sets. Okay, so just the B is the collection of all sets that just have one point in them. Okay. Is B a basis? So the first requirement that we want to look at is that every point should be in one of these sets. So let's let A be an X. Then A is an element of the set containing A, which is in B. So yeah, they each are basically their own little set. Each point is its own little set. And so every point is in one of the sets. We have full coverage because every point is in its own little set. All right, next. Let B1 and B2 be in B. So by the format of sets in B, B1 has to look like some set containing the point A1, and B2 looks like some point containing the set A2. And I mean, if they're equal, then their intersection is just themselves. That's kind of trivial. And if A1 does not equal A2, then B1 intersect B2 is empty. So there cannot be any point C in B1 intersect B2. Because the statement for the second part of the definition is that if you have a point C in the intersection, then something happens. Well, that if part never gets satisfied. So that second statement is trivially true. If C is in the intersection, then blah, blah, blah. Well, the if part is false. So the second statement is trivially true. Okay. So this is also a basis. Okay. Thank you for listening.